Hello everyone, and welcome to tonight's webinar, The Next Generation Science Standards and Middle School Chemistry. I'm Kim Duncan, a Senior Professional Learning Associate for AACT, and I'll be moderating this event. During tonight's presentation, you'll hear from James Kessler, who is the Manager of K-8 Science in the Education Division of the American Chemical Society. You'll find this presentation and other downloads in the handout section of the control panel on the right side of your screen. If you have a question at any point during the presentation, please type it into the question panel. If it's a question related to the content of the webinar, I'll address as many as time permits at the end of the talk. If it's a technical question, I'll do my best to provide you with assistance. For whatever reason, if you are disconnected during the webcast, please log in again according to the instructions you received earlier. AACT members can access the archive of any of the webinars on the Professional Development page of our website. To learn more about AACT and become a member, please visit teachchemistry.org. This webinar will also be posted on middleschoolchemistry.com. And now we'll hear some tips from James about how the lessons in middleschoolchemistry.com can help students achieve the performance expectations described by NGSS standard MS-PS1-4. Go ahead and take it away, James.
Okay, thanks, Kim. Hey, hi, everybody.
Yep. Go ahead and start.
Okay, I am starting. Can you hear me okay? Hey, everybody. Thanks a lot for signing up and attending our first webinar on the NGSS and middle school chemistry. Like Kim said, tonight's webinar is about the NGSS standard MS-PS1-4. That's a middle school standard from Structure and Properties of Matter. And I'll just read it really quick. It's develop a model that predicts and describes changes in particle motion, temperature, and state of a pure substance when thermal energy is added or removed. Now, you know, that's a mouthful, but let's go through what that standard means, and we'll take a look at where we go from here. So it's a performance expectation. All the standards in the NGSS are performance expectations. So that means that at the end of middle school, a student should have certain understanding and abilities based on this performance expectation. This is what we want them to know and be able to do. So the question is, how do you, as a teacher, help the students get there? Where do you start with a performance expectation like this? Well, like in any part of the NGSS or in any standard of the NGSS, you start with the foundation boxes. We can look down here to try to figure out what they're getting at with that long and somewhat convoluted MS-PS1-4. So let's take a look first at the disciplinary core ideas. Down in the disciplinary core idea foundation box, you can find the elements that are used in that particular performance expectation. I won't read them completely verbatim, but they're basically that gases and liquids are made of atoms and molecules. Then they talk about that in a liquid, the molecules are in motion and in close contact with each other. In a gas, they're spread apart and just bounce off each other. In a solid, you know, we always say that they're vibrate in fixed positions. So, you know, they're close together and vibrating. They don't move past each other. And then it talks about changes of state, which occur with as the temperature changes and pressure too. We're just going to talk about heating and cooling as that affects changes of state. Well, so, there's another one. If you look further down, if you printed out the standards, you have something called definitions of energy is also one of the disciplinary core ideas referenced in MS-PS1-4. And there's two big bullets. They're kind of a bit complex. What we did was we kind of treat a simplified version of these. Under definitions of energy, really what we're going to talk about is the term heat, that it's used to mean the, energy transferred due to a difference in temperature, And we're also going to talk about what temperature is, that it's a measure of the average kinetic energy of particles of matter. Down in the foundation box, it says that these are secondary to MSPS 1.4. The reason for that is that they're also treated in another topic within middle school, within the middle school standards, and that is the topic of energy. So you could treat them directly there if you're doing lessons specifically about energy, but since they relate to what we're doing here in MSPS 1.4, they call them secondary, but we're going to treat them like normal disciplinary core ideas. So let's keep going. So the main ideas that you're looking for in this standard, in the disciplinary core ideas, are stuff that you probably already teach. That solids, liquids, and gases are made of atoms and molecules. We talk about the arrangement of the particles in solids, liquids, and gases. That if you add and remove energy, it's going to affect the movement of the particles. And these energy ideas, the temperature is the average kinetic energy of molecules, and that heat is energy transfer due to a difference in temperature. So like I said, you probably already teach these, but what we did in middleschoolchemistry.com is we tried to do it in a way that kids could observe a phenomena, come up with some questions, investigate the questions, and model on a molecular level what the atoms and molecules were doing. The teacher helps explain that. Well, you'll see as we go along. Now, one thing that we just looked at the disciplinary core ideas, but the performance expectation, MSPS 1.4, or any performance expectation, also looks at the science and engineering practices and the cross-cutting concepts. What they do in the standards is they take elements from each one of these foundation boxes and try to combine them in a statement that includes all three. And in this case, the science and engineering practice that's part of MSPS 1.4 is the idea of developing a model to predict and describe phenomena. And the cross-cutting concept is that cause and effect relationships can be used to predict phenomena in naturally designed systems. Basically, if you read MSPS 1.4, it's not that clear what the cause and effect, it doesn't say cause and effect, but it does talk about the motion of atoms and molecules being affected by adding or removing energy. So there's a cause and effect idea in there. So when you do any kind of lessons with students, sort of in the vision of these standards, you should try to incorporate all three of these elements from the foundation boxes so the kids do a practice while they learn an idea and sort of recognize a cross-cutting concept. So the standard itself says develop a model that predicts and describes changes in particle motion. Well, so what do? There's lots of ways to develop a model. But for the purposes of the NGSS, developing and using models really is to predict or describe phenomena. That's the idea. We wouldn't want to begin by having kids make models of salt or water or anything else. There's got to be a reason. So the idea is to start with an investigation. We're going to look at a phenomena that students will be familiar with, and then have students engage in a practice, a science practice, an investigation, so that they can sort of explore the disciplinary core idea and model for a reason. They're going to use these models to understand their observations. So let's go. This is from Chapter 1, Lesson 1 of middleschoolchemistry.com. The idea here is to use a very simple set of materials to get kids thinking about matter on the molecular level. So basically, we just put a few drops of water together on a piece of wax paper. In this case, we put the wax paper on a piece of cardstock. And we have the kids tilt it, move it around, talk about their observations. We see if they can split it with a popsicle stick, more or less into kind of equal-sized drops. It's not so easy to do, but eventually they can get it. And the idea is you're going to ask students whether it was difficult or easy to separate the drops. If water was made of tiny particles, extraordinarily tiny particles, based on this observation, or these observations, would you say that the particles are attracted to each other, repelled by each other, neutral about each other? And students would probably say they're attracted, and then you would get into a discussion about why. All this is to begin thinking about matter at the very, very tiniest level, the molecular level. So then we do another quick demonstration. We put a drop of food coloring in water and just let kids observe, and you ask them, why would it be that the food coloring moves? Why doesn't, does it just stay at the top? Does it just go to the bottom? Does it all stay together in a clump? Why would it move like this? And the idea is to try to get kids to think that there must be something going on in there other than just the water molecules sitting still. So you want to be able to guide them or tell them that, believe it or not, the water molecules are actually moving in there. That not only are they attracted to each other, like we saw in the drop of water, but they're in motion. That's hard to believe. So we use a lot of molecular model animations in middleschoolchemistry.com to help kids visualize what is happening on the molecular level. Let's just take a look at this one really quickly. The idea is that this is a sample of water, and that these represent water molecules. Now, this is only Chapter 1, Lesson 1, and all throughout Chapter 1, we represent molecules or atoms, either one, as just small spheres, just moving spheres. We get into a little bit more of the structure of a water molecule in Chapter 2, you'll see later. But right now, this is the look that they get. And the idea is that particles are close together because they're attracted to each other, and they're moving. That's why that drop of food coloring, which was also made out of particles, if you could imagine dropping a bunch of small little food coloring molecules in maybe very dark blue, they would get knocked around by all these particles and eventually mix throughout. That's the kind of discussion you would have with students. We also always give kids a chance to draw, make their own drawing, use their own captions to sort of describe what you describe to them, so that they kind of internalize it more. They don't just watch the video. They make their own drawing. In this case, we use motion lines. 2 motion lines is like room temperature water. We use 1 for cold water and 3 for hot water. It's just an easy way for kids to make their drawings. So then in Chapter 1, Lesson 2, we ask, like, what we think is a reasonable next question is, if you wanted water molecules to move faster, what could you do? And kids might say, well, you could, mix the water around or shake it up. But eventually, we want kids to be able to say that, hey, maybe if you heated it, the water molecules would move faster. And if they don't come to that, you can suggest it. Did you ever notice when you put water on the stove, does it seem to move faster, slower, stay the same? This idea that heating increases molecular motion. So if the kids say, okay, they agree with you that maybe heating increases molecular motion, we would ask, what could you do here in the classroom to test and see if that's true? So at this point, we're starting on down a road of having kids help you design experiments to answer a question. So a question is, does heat, or does adding energy or heating increase molecular motion? So you would go through a process with students to come up with an experimental design to see if that's true. Now, they've already seen a drop of food coloring in water, so maybe they would suggest use hot water and see if it moves faster. And of course, you would say, well, should we just use hot water, or do we need something to compare it to? And this whole idea of having a control, or having 2 samples so you can actually tell if there's a difference. So in this case, you would go through that whole idea of asking kids, would you use the same amount of water in both cups? Would you use the same type of cup? Would you use the same food coloring, and why? Would you drop them from the same height, and all that? So eventually you get to a test where you might put, we put yellow and blue food coloring in cold water and hot water at the same time and see if there's any difference. And there's a clear difference if the temperature difference is large enough. And on here you can see that the hot water is on the right and the cold water is on the left. And it's pretty good evidence, because it was a fair test, that heating or adding energy increases molecular motion. That's why it's mixing a lot faster in the one that was hot. So the question is, can we visualize that on the molecular level? Like, what's really going on down there? This is related to the, obviously related to the drawing they did before. Let's just see. If we look at another animation, on this one, here, there's cold water, let's say, and we're just going to warm it up. And if we add energy or heat, this water, we want kids to see that it increases the molecular motion. And you can go back and forth a couple of times so they really see the difference. We also want them to see that the particles are a little further apart also. You can see a little bit more blue behind there, because the idea is this extra motion competes with the attractions of the water molecules, and they get a little further apart when they move faster. So kids get a chance to draw this. Here is room temperature, and they can draw the particles a little closer together with one motion line, and here a little further apart with 3 motion lines, and write captions beneath so that they are doing, the drawings. They're hopefully thinking about what they're saying and not just, listening or watching. So this leads us to Chapter 1, Lesson 3 about thermometers, and why do they act the way they do? Does anything about a thermometer have anything to do with this idea of molecules? Well, we have kids put a thermometer in cold water and the same one in hot water, and just watch. They know what's going to happen. They watch the red liquid go up and down, and you point out to them that it's a liquid, that it's alcohol, it's made out of molecules. So what's happening in there? So we take another look. All these animations are on middleschoolchemistry.com, incorporated into the lessons, so that when the kids investigate a phenomena, they can, or you can help them understand it on the molecular level. So that's at room temperature. So if you put the thermometer in cold water, it cools the liquid in the thermometer. The molecules move slower. They get a little closer together, and they move down the thermometer. If you put it in hot water, the liquid in the thermometer gets hotter. The molecules move faster, get a little further apart, and move up the thermometer. And like in every other time, there's an activity sheet where kids can draw a model themselves and describe what their drawing is. Now, the reason why we're doing all this is because it's directly related to the standard in MSPS 1.4. We're getting to the idea that substances, whether they're solid, liquid, or gas, are all made up of atoms or molecules, that adding heat or taking heat away affects the molecular motion, and we're sort of laying the groundwork for understanding state changes, which comes later in the performance expectation. So we've only dealt with liquids so far. So let's, in Chapter 1, Lesson 4, we had this famous ball and ring experiment. You've probably seen it before or done it yourself, but the idea is that the ball moves through the ring. It's a close call, but it goes through. And then you heat it. You need a pretty good heat source, like I have a little portable Bunsen burner. And then you try to put it through the ring again, and it doesn't go through. And the question is why? And then if you cool it, we just cool it by putting it in room temperature water. It goes, let's see, it goes through again. So does this have anything to do with what we know so far about atoms or molecules or molecular motion, heating and cooling? Well, let's see. So here we have like this is an anvil, which many kids won't know what that is, but tell them it's a very big piece of metal. And that if you heat this solid, the particles move faster and get a little further apart. That's just like what, very, very similar to what happens in the gas, in the liquid. Except in this case, none of the particles move past each other. It hasn't melted. It's just getting hotter. So when a solid gets hot, the particles vibrate faster but stay in a fixed position unless they eventually melt. We'll get to that later. And as in every other lesson in middleschoolchemistry.com, there's a student activity sheet, and again, they can make their drawings and write captions, and you can go around the class and see, who really understands this and who needs some help. We also need to talk about gases because in this particular performance expectation, it talks about all the states of matter, solids, liquids, and gases. So, at middle school, maybe students understand that gases matter, but you might need to drive that point home. So we have you can do this experiment in class, or you can show the video, but we deflated a basketball and put it on a scale, and it weighs about 576 grams. And we want you to really be able to see that, 576 grams. And then we pump it up and put some just ambient air, good old air in there, and it goes up to 581. So it was at 576, it goes to 581. So we put about 5 grams of air in that basketball. So this whole idea that matter has mass and takes up space, we took up the space in the basketball, it has mass. You could make a pretty convincing argument that gas is matter. So then we're going to go through the same process we went through before. We need to heat and cool a gas. We heated and cooled a liquid, a solid, and now we're going to do a gas. Oh, sorry. First we're going to look at the difference between solids, liquids, and gas because we've looked at all of them. So now a solid, the particles are very attracted to each other. They don't move past each other. This is just at room temperature. And we're not changing the state of these. We're not saying this is a solid and then we're like heating it to make it into a liquid. No, we'll do that later in state changes. Right now we're just saying here's a solid at room temperature. Your solids, the particles are in fixed positions and vibrate. Here's a liquid at room temperature. They're different. The attractions aren't as strong as they are in a solid, so they are able to move past each other. And then at room temperature, a gas, the attractions are quite weak, and they're very spread apart. When they hit each other, they just bounce off. So those are the ideas behind the arrangement of the particles of a solid, liquid, and a gas. Now let's just go to where we heat a gas. We take a little bottle here, and it's empty, except for the gas that's in it, naturally. And we dip it in a detergent solution and then put the bottom in hot water. You see that a bubble forms. And students and teachers, everybody loves this activity. And then you put it in cold water and the bubble goes down. So the idea is that, just like in every other case, that adding energy or taking energy away affects the motion of particles, whether it's a solid, liquid, or a gas. So let's see what's happening here. So again, we have an animation that helps kids understand what's going on. Well, first we show them, okay, this is a gas, that if you heat it, the particles move faster, and that in this case, a balloon would expand. Let me see. Let's try. Okay, okay. I thought this was another animation, but this one was fine. It shows that heating a gas increases molecular motion and blew up that balloon a bit. Let's see here. So in this case, you can go to the student activity sheet and show that you've got outside air pressure on the top of the little bottle with the detergent solution on it. You put it in hot water, and the particles on the inside move fast, and the pressure they put on that bubble film overcomes the air pressure on the outside, and it pushes it good and hard because of the fast-moving particles, and you get a bubble. But then, if you put it in cold water, the particles on the inside slow down, they don't move as fast, but the outside air pressure is the same, but now that's greater than the pressure by these slower moving particles, so now the outside air pressure pushes the bubble in. So that's what's going on with that's the way the heating and cooling affect the particles of a gas. So at this point, we've covered kind of a lot of what's in MSPS 1.4. The students used their a science practice of developing a model to predict what would happen and to describe what happens when they heat and cool solids, liquids, and gases. It's a good start. So what do we do now? Well, we need kids to go a little bit further because they need to look at state changes. According to MSPS 1.4, it talks about developing a model that predicts and describes changes in particle motion, temperature, and state of a pure substance when thermal energy is added or removed. So let's keep going. In Chapter 2, Lesson 1 is about conduction. So we want to finally get to this idea of what is this difference between heat and temperature. It's one of the disciplinary core ideas under definitions of energy. They talk about that heat is a transfer of energy because of a temperature difference. We want to try to show that. We also want to try to show what temperature is. That is the average kinetic energy of the particles of a substance. But how can you do that? So here we have, what we did was we took some washers, and they're just at room temperature. You see they're about 24, maybe 23, 24 degrees centigrade. But we put them in very hot water. Water over, let's see, about 50 degrees, well, whatever, almost 50 degrees centigrade. But you watch that the temperature of the water goes down. And this doesn't take long. We have it in real time here, and then I think it's even a little lower after some time passes. So the question for kids is, why did this happen? Why did the temperature of the water decrease when we put those room temperature washers in there? We also, it's not shown here, but we also have the kids take the temperature of the washers afterwards. So the temperature of the water goes down, the temperature of the washers goes up. So the question is why? Why does this happen? And we use the analogy of putting like a spoon into hot soup. And if you're not careful, you know, that spoon can burn your mouth because it gets pretty hot. Even though it started at room temperature, you put it in the hot soup, somehow its temperature changed. So we have a little animation that attempts to show this. The spoon goes into the hot water. Originally the spoon is just at room temperature, but now this water here, the particles are moving really fast and they're transferring their energy to the spoon. So now the spoon's particles are increasing in motion. It's heating up. So we try to show kids this idea that energy can be transferred through conduction, through contact, and that's what heating something means, that you're transferring energy because of a difference in temperature. The spoon was room temperature to begin with. The soup was hot. So the heat moved, or you could say the energy was transferred from something that was hotter, the soup, to something that was cooler, the spoon, and heated it up. And as always, we use the student activity sheet for kids to make their own motion lines to show what happened. In this case, the before case would be room temperature spoon, hot soup. You put it in. Now they can show that the spoon is a little hotter, they'd use more motion lines, and the soup is a little cooler, so they'd use fewer motion lines. Well, this idea that heat is energy transfer because of difference in temperature, so I guess that brings up the question, so what's temperature? So we have, in middleschoolchemistry.com, we used to have a link to a temperature simulation, but it no longer works. It was on another site. And we're getting our own produced, but we're not quite there yet. But I just want to show you quickly here what we're trying to do. I'm going to come out of the PowerPoint for a second and just bring up a new simulation that I hope will be on the site soon. So I'll just bring it up really quickly. Here, the idea is that the particles of a substance at any temperature, well, the temperature is the average kinetic energy. So not all the particles are moving the same speed. Like on this one, if you notice, what we tried to do is show that when particles hit each other, some of them transfer enough energy that the color changes a little bit. You might see that some look a little bit purple because they gained enough energy to have enough speed that we changed their color. I'll show you here. Let's go to hot. Here, the particles are, a lot of them are red, which means that they're hot, and many are pink and a few are purple, but not that many are blue anymore. So this is, I think, a nice simulation because it shows that the temperature is the average kinetic energy. They're not all red. They're not all going at the same speed. They're going at different speeds. And then at medium, they are also a combination of speeds. So anyway, we want kids to know that temperature is the average kinetic energy of the particles of a substance. That's a pretty big idea in energy. So I'm just going to, let's see, pause this and put it back down there and come back to the PowerPoint. So that would be all this to lead up to how do state changes work. So a very common state change is evaporation. So we use that one. I mean, it's a classic, and it's the right way to go to get kids thinking about state change. So what we do in the beginning of the activity is moisten a paper towel and hang it up in the beginning of the class, and then ask kids what they think is going to happen, and by the end of class. And then a lot of kids will say, maybe it'll dry out, maybe it'll dry out partially, and you ask why, and they say because that's what things do. And you ask for examples of evaporation, and they may give you lots of examples from their daily life about puddles drying up or putting clothes on the clothesline, if people do that anymore. So then the question for kids is, okay, all that's good, but how can you make things evaporate even faster? And, I think most kids know that if you heat them up, they'll evaporate faster. And if someone suggests that, you ask for examples, and some kids will say that puddles dry up faster on a hot day than a cold day, and or if I use a blow dryer on my hair and put it on hot, it gets drier faster, or put clothes in the dryer, they don't just spin, they also get heated up. So there's a good reason to believe that. But then you would ask, well, how could we actually test that here? So they've already seen you put water on a brown paper towel, so maybe there's a way to use that. So anyway, what we do is we have kids put a little bit of hot water. You don't need much. This picture implies that these things are full of water, but they're not. You only need like maybe a fifth of a bag of hot water and the same amount of room temperature water. And then you have kids put a drop of a drop of room temperature water on each of 2 pieces of brown paper towel, because you want this to happen pretty quickly, so you only use a drop. And then you move them to these hot bag and room temperature bag, and you just observe. Now, let's take a quick look at a molecular animation to show what's happening here. In this case, here's the hot one, here's the room temperature one, the brown paper towel with the drop of water, and this shows that on the hot a bag, the water molecules are moving faster. They have more likelihood that they'll break away from each other and evaporate. Here they're moving more slowly on the cold bag, and they stick around longer. They don't evaporate as quickly. And like we've said before, kids get a chance to draw that and to write captions to describe what they're drawing. Now, while kids are doing that activity, there's a certain amount of waiting, not a lot usually, but a bit of waiting for the water to evaporate. So you can take that opportunity to show some more classic looks at how water molecules are depicted. And this is the first time we've gone away from this just a sphere idea of an atom or a molecule. So we've got an animation that just shows these different looks of water. Like here's the ball and stick model, and this is called the space filling model. We use this one a lot in middle school chemistry, and it began with this with the idea of H2O. And what are those H's? What is that O? So these are two hydrogen atoms, and this is an oxygen atom, and it ends up to be this pretty traditional look of a water molecule. So you could show students that, and sometimes we try to get kids to understand that although we've got all these models, and water molecules aren't just small like a dust particle or like a grain of salt. I mean, they are small, like beyond your ability to comprehend. I mean, really small. We have a factoid we usually tell students, or we include it at middleschoolchemistry.com, that, if you took about a tablespoon of water and you could count the water molecules at 1 million every second, it would still take you about 190 million centuries to count all the water molecules in that small volume of water, in that tablespoon, more or less. That's 19 billion years at 1 million a second. So these are so extraordinarily small, it's hard to comprehend. In Chapter 2, we do begin to introduce kids to the idea that water molecules, they're attracted to each other, just like we saw in Chapter 1, but there's a reason. It's because because the way that the hydrogens are bonded to the oxygen, they've got a little bit of positive, they have a slight positive charge down here in this part of the molecule near the hydrogens, and a little negativeness up here toward the oxygen. We don't spend a lot of time talking about that because we cover it in detail in Chapter 5, this idea that water is a polar molecule. But at least we introduce the idea that there's a reason why they're attracted to each other, that the positive part of one is attracted to the negative part of the other, and it's a sort of begins to set the table for what they'll learn later. And here, this is just a kind of a cool way to visualize liquid water, that the water molecules are close together, but they're in motion, and it's more, arguably more interesting than the single spheres that they've seen before. And, by this time, their paper towel on the hot water has evaporated. And one neat thing about brown paper towel is that when it gets lighter in color, you can tell that there's less moisture on it. So it's pretty easy to tell that water has gone. Now this, we included this, which is the like water vapor. It's after water has evaporated, it's in the gas phase, and a state change has occurred. But one nice thing about this is that it shows that the water molecules have, separated from other water molecules, but any single water molecule doesn't come apart. It doesn't come apart into the oxygen and hydrogen atoms. It's just that the molecules themselves separate from other molecules. That could be a misconception by students that the water molecules themselves come apart into the atoms that they're made of. We also have kids make physical models, this classic styrofoam ball thing. And that's because eventually we have the kids physically move them around and agitate them to the point where they model that that they leave the liquid state and become a gas, so that they can sort of physically do the evaporation. So then we go on, Chapter 2, Lesson 3 is about condensation. And we're almost to the point where students should be able to talk in terms of molecules moving faster when we heat them, slower when we cool them, maybe getting a little closer together when you cool them because of attractions, getting a little further apart. So these ideas are all sort of come together from chapters 1 and 2 to give a good picture of the motion and arrangement of particles of solids, liquids, and gases, and state changes. Now, this one, it's not a video. This just shows our setup. What we do is we just show kids, if you take some hot water and put it in a cup and stick another cup on top, pretty quickly the top cup becomes all cloudy looking. And if you look closely, we ask students to, what is that cloudiness on the inside of the top cup? And, you can tell pretty easily, either with a magnifying glass or by taking that top cup off and putting your finger in there, that it's water. So we ask, where did it come from? How did that happen? So some kids may know about the water cycle, and they know that when there's evaporation, there's also condensation. And we ask them about examples of condensation, which are usually a little harder for kids to come up with than evaporation. But some kids might say the moisture on the outside of a cold, like soda can or bottle or glass. In the summer, sometimes when it's more humid, depends where you live. But so we sort of talk about, like, why do you think that happens? And we get responses from students, and you can show them that, in this case, if you put that top cup on top of hot water, it'll get cloudy. But what's happening? Well, what happens is that some of the water vapor, the gas that's up in that top cup, slows down. Let's look at it one more time. Here, these are the water, the vapor that's in the top cup, but then it strikes the side of the cup where it's a little cooler, transfers some of its energy, more water molecules do that, and they eventually come together. Now that, the way we showed it there, it looks like almost like it's a little tiny solid. It's not perfect, but it gives the idea that the water molecules slow down, come together, and become liquid water instead of water vapor. So then we ask kids, well, let's do the opposite of what we did before. Before, we had liquid water, and we wanted to see what do you have to do to increase the rate of evaporation? So you have to heat it. Well, in this case, we have water vapor, a gas. What do we need to do to increase the rate of condensation? So they can guess that you'd have to cool it more. So just like many other lessons in middle school chemistry, we asked them for experimental design. How would we do it? Well, we need 2 samples of water vapor, but we cool one of them, but not the other. And when you look closely, after a couple of minutes, you wipe off the top of these cups and you look, and the one that had the ice on it, the drops are bigger, there's more water, there's more condensation occurred because we cooled it. So this, performance expectation, MSPS 1.4, develop a model that predicts and describes changes in particle motion, temperature, and state of a pure substance when thermal energy is added or removed, is pretty well covered by the lessons in chapters 1 and 2 of middleschoolchemistry.com. I guess what we saw was that students explored the meaning of heat, and temperature, energy transfer, and changes of state. We looked at evaporation and condensation, and we used the ideas from chapter 1 about particles gaining energy and moving faster and further apart. That's what allowed them to evaporate. And particles losing energy or cooling, slowing down, getting closer together, and that's eventually leads to condensation. Now, I need to ask Kim how our time is, and if we should stop here or show a couple more animations. We could stop for questions. Kim, how do we look?
I think we probably should stop for questions. So what I'd like you to do is forward to that last slide with the links.
Okay. Forward to the last slide with the links. I can do that.
Yes, just keep hitting the arrow.
I know. I could come out.
No, go ahead. Yeah.
Oh, okay. I'll come down to here. Right here?
Perfect. Perfect.
And then I will come back in.
All right.
Okay.
So thank you. Before we begin our Q&A, I'd like to take a short break and ask everyone to complete a brief questionnaire about the webinar at the link shown on their screen. This will also allow you to generate your certificate of attendance if you'd like one. This is also a good time to send any questions that you might have for James to me. We're going to begin the Q&A in just a minute or so, but before you go ahead and go to that link, I'd like to point out to you that if you look in the handouts section of the control panel, you will find a download that shows exactly how the lessons in middle school chemistry, the first 2 chapters, are directly aligned with the performance expectations in middle school MSPS 1-4. So go ahead and send in your questions and take the survey, and in about 2 minutes we'll open up the questioning. I already see bunches of questions running in. All right, James, I'm going to start with some questions. The first is from Heather, and she said, do you believe that students need to learn and have an understanding about atoms prior to learning about the molecular arrangements and motion in solids, liquids, and gases?
Okay. I guess it depends on, can you just read the first part of that question again?
Do you believe that students need to learn and have an understanding about atoms before they learn about the prior to learning about the molecular arrangement and motion in solids, liquids, and gases?
I guess no. If the question means that the learning about atoms, like about the substructure of atoms, like, that they're made of protons, neutrons, and electrons, or that they have, energy levels or things like that, no, I don't think they need to know that at all. In fact, when we designed the Chapter 1 of middleschoolchemistry.com and only used spheres, whether it's an atom or a molecule, we did get some pushback. I hope I'm answering your question, but we thought that that was kind of irrelevant, the actual structure of an atom or a molecule. For the purposes of, understanding the arrangement of the particles in a solid, liquid, or gas, we felt that a sphere was good enough for kids to start. The main idea being, as you know, that they're, that in a solid, the attractions are strong and they're close together and they don't move past each other. In a liquid, the attractions are not as strong, so they are able to move past each other, but they're strong enough to keep them near. They don't just fly away like a gas. And in a gas, the attractions are very, very weak, and so they're far apart. They barely interact at all. I think you can get those points across with just spheres, so that's the direction we went.
Awesome. There was a second question. I think it's very related to that. It's from Sharon. She said, should we talk about atomic structure before talking about phase changes? Can you...
Yeah, I think it's the same answer, really, at least to us. And it seems like to the writers of the frameworks and eventually the standards based on the frameworks, they use the term particle in the most basic, like in this one, in MSPS 1.4, for instance, develop a model that predicts and describes changes in particle motion. I think that they're satisfied that if you can get that idea across, that adding energy or heating increases molecular motion, or whether it's atoms or molecules, it doesn't matter, they're all particles, that you're good. That it's not important to know the structure of the atom before you go there. In fact, it might even be counterproductive. It seems like it's it's too much information. You don't need that, I think.
Awesome. All right. Here's the next one. It said, in saying that students explored temperature, I noticed there wasn't much of an explanation about kinetic energy. Do you feel as though it's necessary to ensure that students have an understanding of kinetic energy in order to understand temperature as it relates to the motion of the particles?
Yeah, I guess, I think in middleschoolchemistry.com, when we had our link to the simulation that worked for a long time and doesn't work anymore, in that part of the lesson, we talked about that any object, no matter how big or small, no matter how small or large the mass, if it's moving, it has kinetic energy. So I didn't talk about it. You're right. I didn't talk about it in this presentation, but we do deal with it in middleschoolchemistry.com. Not a whole lot, but we say there's something called kinetic energy, the energy of motion of any object that has mass. So therefore, all these tiny particles have kinetic energy, a certain kind of energy. And that's the energy that you can actually detect with a thermometer. It's thermal energy is the kinetic energy. So, yeah, we talk about it. I guess the idea that the faster something moves, the more kinetic energy it has, and the higher the temperature, when you're talking at the molecular level, I think that all can make sense. I don't know if I answered your question, but yeah, I would say that talking about kinetic energy at least a little bit might be useful so they have an idea of what you're talking about when you use the term, when you show that simulation.
Awesome. Thanks, Jim. Here's another question. It says, I see that there are student readings. Do you assign those before or after you do the activities?
Yeah, good question. The student readings are all at the chapter level. So we're assuming that, they're also reading, every lesson has reading associated with it because each one has an activity sheet. But the student reading that you're referring to is at the chapter level. So we would do all the lessons and anything else you want to do with students in class that relates to observing phenomena and investigating. And then we have kids do the student reading because it refers back to what they've done in class. It's designed to go after to sort of, confirm what they've done, refresh your recollection, make connections to stuff that now you might understand better having done the experiments. So yeah, after.
Awesome. Here's another one. Where can I purchase the small thermometers?
Good question. We got these years ago from a company called Down East, which I don't even know if they exist anymore, and they didn't manufacture them. They're not that easy to find. So to answer your question, we are using thermometers that we've had for years. And if you go online, to the standard suppliers, Sergeant Welch or Carolina or Flynn, you may get lucky and find something real similar. But I'm not sure how easy it is to find these anymore. Sorry about that.
Okay, maybe I'll try to look that up tomorrow and we can post something on the website if I can find it.
Oh, wow, that'd be nice.
One more. How hot should the hot water be? I don't have hot water available in my room. I'm going to have to use a microwave to heat it.
Well, one thing that I have done, that is, I went to Target and I just bought a small, what do you call this thing? You plug it in and you put, whatever, like 4 or 5 cups of water in, and it heats up really fast and pretty darn hot. I mean, you got to actually be a little bit careful. But I've used that for small conferences where we do professional development conferences with teachers, and I don't want to bring like a big coffee urn or they don't have a good system for getting hot water. I just bought one of those. They're like, I don't know, it was some ridiculous thing, like less than $10, and it works great. Another possibility is if you heat water and put it in a pretty good thermos, not a little thermos like you would use for your lunch, but something bigger, that stays hot for a long time if it's a good one. So I brought hot water from home. I've heated it up in the classroom with one of those, cheap plug-in water heater kettles kind of thing.
Mm-hmm. All right, we have a suggestion from Sharon. She said that you can use fish tank thermometers from Walmart for those little thermometers. Have you ever seen those?
Are you asking me?
Yeah, you.
Oh, sorry. No, I don't know. We have not had to make any purchases like that, but it's definitely worth checking out. I just don't know.
All right, Jim, what I'm going to do is turn the presentation over to me because I want to show the people that are still left the alignment that we put together and that's located in the handouts and on Dropbox. So can you shift? There we go.
I can try.
All right. Can you see my screen at this point?
Yes.
All right. So I just wanted everybody to see this alignment sheet that we put up. You can see that we made it the same colors as the NGSS alignment, and it shows which lessons help your students to meet those performance expectations for each one of those different ideas. So anyway, that's all the time we have. Thanks again, James, for a great presentation, and thank you all for being a great audience. Our next webinar takes place on Wednesday, November the 4th, when Laura Trout, who is Dean of Curriculum, Science Department Chair, and Lower School Science Specialist at Lancaster Country Day School, will give us an introduction to POGLE, which is Process-Oriented Guided Inquiry Learning. Remember that to receive a certificate of attendance for tonight's webinar, you'll need to fill out the post-webinar survey at the link shown on your screen. You'll also receive the URL for the survey again in a follow-up email. Please visit teachchemistry.org to browse and register for our upcoming webinars. Thanks again for attending, and good night.